In this video, we're going to continue our discussion about the unit circle, and we're going to see how we can solve different types of questions involving the unit circle. Now, for this part of the unit, Unit 1, Part 3, we're stepping away from applied problems specifically for the time being, and instead talking about the solutions to different unit circle components in a theoretical or mathematical sense. We will see how these apply again, but for the time being, we're just focusing on some mathematical computations first. Now, normally in class, I would have you complete this unit circle as a quick quiz to see if you can do that in under 5 minutes. I would recommend that you pause the video and try that now, obtain a blank copy, and give yourself 5 minutes to complete it. Resume video playback in a moment after you've tried that. Now, hopefully you were able to do that in under 5 minutes because you've been practicing. Here's a quick view of a completed copy from the other day. Hopefully you can read that on your screen. You can check your work against this. Now back to our lesson for today. Here's just a quick reminder of the definition of our 6 trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. Now each of those trig ratios are defined here in terms of side lengths of a right triangle. What I would like to remind you of is that these same side lengths can be determined by angle measures within a unit circle. So again, imagine that I had a triangle inside the unit circle that was placed here at the 30-degree angle measure. Well, the right triangle associated with that in this position contains an opposite side length. We'll call that one y because it corresponds to the y coordinate. And adjacent side length, we'll call that one x because it is the x coordinate of this position. And then the hypotenuse length is always 1. So if we substitute those known values in each of these definitions, we might say that sine is equal to y divided by 1, or in other words, sine is just equal to the y component of the coordinate. Cosine is going to be x over 1, and tangent is y divided by x. So again, if you can memorize the positions of each of these coordinates, then you could also calculate trigonometric results for angle measures at specific positions around the unit circle. And to extend our knowledge just a little bit further, not only can we answer questions about sine, cosine, and tangent, but also cosecant. That's going to be 1 divided by y because it's the reciprocal of sine. Secant is going to be 1 divided by x, and cotangent is going to be x divided by y. And again, these letters x and y are representing the x and y coordinates of the positions around the unit circle. Memorizing and recognizing these results in the reciprocal functions is going to be particularly helpful when we talk about graphs of trigonometric functions in a few weeks. So let's consider an example here, a mathematical example. There might be an application to this somewhere, but for right now we're just talking about this from a mathematician's perspective. We're told that sine of theta is going to equal radical 5 over 5. I don't know what the angle measure theta is, and I'm not really solving for theta in this particular case, but I'm told that sine of theta will compute to be square root of 5 over 5. I'm also told that cosine of theta, again, the same theta angle, the same angle measure, this time is going to be equal to 2 radical 5 over 5. Our objective in this question is to find the value of each of the 4 remaining trig functions of theta. So again, this question is not asking us to solve for theta, but to find the values of the trig functions evaluated at theta. So what I would do in a problem like this is I would write them down. I would write down sine theta, cosine theta, tangent theta, cosecant, secant, and cotangent. And we know what sine theta is. That's radical 5 over 5. And we know what cosine, sorry, did I say secant? I meant sine. We know that sine theta is radical 5 over 5. We know that cosine is 2 radical 5 over 5. Now, what we have to do is find the results of the remaining 4. And we can actually do that pretty easily. In this particular example, a blank triangle was provided, but even if that wasn't provided, I still think you can answer this question. And what I would recommend if a triangle isn't provided, I would try to decide which quadrant we're working in initially. you'll notice that sine is reported as a positive number. So with sine being positive, sine is positive in the first quadrant and in the second quadrant. Cosine is also being reported as a positive number. So cosine is positive in the first quadrant, and cosine is also positive in the fourth quadrant. We talked about that when we designed the unit circle. So the only quadrant that contains positive sine and positive cosine results is here in quadrant 1. So if I were solving for theta, I know that theta has to be somewhere in between 0 and 90 degrees, or somewhere between 0 and pi over 2 radians. Now again, in this particular case, a right triangle was provided to us, and so the angle measure theta in this right triangle, of course, is going to be between 0 and 90 degrees, or between 0 and pi over 2 radians, because the nature of a triangle implies that the three angles will sum to be 180 degrees, and if one of those angles is already 90, then the remaining two angles, alpha, beta, theta, whatever you want to call them, these two angles must be less than 90 since they have to add up together to be 90 degrees. So I may have gotten off course just a little bit there. I'm going to erase this because they're not really necessary for this particular problem. And I'll just start answering this problem with the given information. Let's remind ourselves that with sine of theta being radical 5 over 5, we should recognize that sine of theta was describing our opposite side length divided by the hypotenuse side length. And so if we're talking about radical 5 divided by 5, then it stands to reason that our opposite side length, the side opposite of theta, has to be equal to the square root of 5 units in length. And the hypotenuse side length would be 5 units in length, according to this fraction. Similarly, cosine theta is equal to the adjacent side length divided by the hypotenuse, which is 2 radical 5 divided by 5. So again, we see the hypotenuse is indicated to be 5, while the adjacent side length is 2 radical 5. So the side length adjacent to this angle measure theta drawn here is 2 radical 5. We were lucky in that both of these fractions indicated the exact same hypotenuse value, but even if the two ratios that were provided did not provide the same hypotenuse value, we could continue to solve the triangle with solve these ratios with a triangle as long as we find a common denominator. If we work to find a common denominator, then we can continue to solve the triangle in terms of those side lengths. Now that we have the side lengths, all three side lengths of this triangle, we can actually answer the trigonometric ratios for each. So recall that tangent of theta is equal to the opposite side length divided by adjacent side length. So in this case, the side opposite of theta is radical 5. The adjacent side length is 2 radical 5. So opposite divided by adjacent gives us radical 5 over 2 radical 5. When we simplify this fraction, we see that the radical 5's cancel or factor out. We're left with 1 over 2. So the ratio of tangent theta is equal to 1 over 2. The opposite side length is half that of the adjacent side length. That's what our ratio is telling us. Now quickly we can establish the cotangent result. The cotangent result is the reciprocal of tangent. We can call that 2 over 1, or better yet, we'll just call that 2. Similarly, secant is the reciprocal of cosine, so we could say that this is 5 over 2 radical 5, and cosecant is going to be 5 divided by radical 5. Now, these results are perfectly fine for me, and I believe they'll be accepted by Math Excel as well. However, it's worth noting that sometimes it's appropriate to rationalize the denominator. In other words, we don't want an irrational number in the denominator of a fraction. And so if we needed to do that, I'll just choose the cosecant result as an example. If I had 5 divided by the square root of 5. That's not rationalized, but we can rationalize it by doing the following. We simply multiply by the value in the denominator. In this case, it's the radical of 5. When doing so, you should note that the square root of 5 times the square root of 5 is equal to the square root of 25. And in the numerator, 5 times the square root of 5, well, that can't be combined because those two are not like one another. And we'll also point out that the square root of 25 is precisely 5. And now we have a rational number in the denominator and an irrational number in the numerator. And this would be acceptable as well. So these two numbers, the fraction we started with and the fraction that we ended with, are the same. They are equivalent. And for me, in most of the work that I assign, this is perfectly fine as an answer. However, there are some times where the rationalized result is needed, and this is how we can obtain that. In the future, if you need a reminder, simply search for this phrase online, and I'm certain you'll find videos that will help you understand that. Now, for the second half of this video, we're again going to go deeper into the mathematical or algebraic construct of this trigonometric components. And we're going to talk a little bit about what we call trig identities. Now, trig identities are algebraic ways to represent trigonometric functions and ratios. And trig identities are what we're going to be focusing on in Unit 4 and 5 of this class. So if you recall, at the start of the semester, I said that Unit 4 and 5 tend to be the more challenging units in this class. This is part of the reason why. We're going to be building algebraic equations using trigonometric functions, and we're going to be analyzing and working with them to solve complicated equations. These trig identities also help us in the future when you get into calculus coursework. So we'll start with some of the basic or fundamental trig identities here. We're going to pretend or let A, B, and C represent side lengths of a right triangle, just like this diagram shows here. So with our angle measure identified in the bottom left-hand corner, B takes on the value of the opposite side length, A is our adjacent side length, and C is our hypotenuse. Let's connect these side lengths of the triangle to a famous mathematical equation. Certainly you all have seen a squared plus b squared equals c squared before. So to create this first identity, I'm just going to do a little bit of algebra. I'm going to divide both sides of the equation by c squared. Now if I divide the left side of the equation by c squared, that would be the same as dividing both of these components by c squared. And this is perfectly permissible because because the two lines are algebraically equivalent. Now what I'm left with here on the right-hand side, c squared divided by itself is equal to 1. And on the left side, I can write this as a divided by c squared plus b divided by c squared. Now to make this a little bit more interesting, I'll note here that a, which was representing our adjacent side length, and c, which was representing our hypotenuse side length, can now be rewritten that way. So I'm going to say that this is the adjacent side length divided by the hypotenuse squared, and b is our opposite side length divided by the hypotenuse squared, and that has to equal 1. And by definition of our trig functions, we said that the adjacent side length divided by the hypotenuse side length is the same as our cosine ratio. So cosine ratio squared plus the sine ratio squared must be equal to the number 1. And it's common practice when writing trigonometric ratios raised to a larger power not to do so inside of grouping symbols like I've shown here, but instead like this. So cosine squared theta plus sine squared of theta must equal 1. This is typically how you'll see expressions with powers written inside of trigonometric functions. Now I do want to point out that most textbooks actually report this trigonometric identity in this order, and I'm not entirely certain why, but this is perhaps a more common way to write it. They usually write sine squared plus cosine squared equals 1. And this is perhaps the most famous and popular trigonometric identity. It's sometimes called the Pythagorean Identity. And hopefully you can understand why, because it was derived from our Pythagorean equation. Now, this identity is particularly helpful if we're working with large equations that involve trigonometric ratios, because we can now make some substitutions. If we ever encounter an equation that contains this phrase, say sine squared of some angle measure plus cosine squared of the same angle measure, theta in this case is the same in both expressions, well, that combination of those two phrases there is actually equivalent to the number 1, and we can replace this expression with the number 1. And it also stands to reason that we could isolate different components as needed. If we see a cosine squared by itself, that would be the same as 1 minus sine squared of theta, and cosine squared could be replaced with 1 minus sine squared. And also we could say that sine squared theta is equal to 1 minus cosine squared theta. Each of these extensions are derived from simply subtracting this cosine squared group to the right side, or subtracting sine squared group to the right side. So all three of these would be considered Pythagorean identities. Similarly, we can apply different algebraic constructs to the Pythagorean identity as well. So I'm going to start off with sine squared plus cosine squared equals 1. And I don't know if you're picking up with the way I'm saying this. I'm saying sine squared, but I really mean sine of theta squared and cosine of theta squared. It's just common nomenclature to abbreviate the phrasing the way I am right now. But if I take sine squared and divide it by, say, cosine squared, and divide everything by cosine squared, that's perfectly permissible, because what I'm doing to one side of the equation, I'm doing to the other, and I'm retaining the balance. You might notice that sine divided by cosine, or our y component in a unit circle divided by the x component in the unit circle, is another way to describe the function tangent. And I'm just scooting up here to remind you, if we had a xy axis, so here's our y-axis and our x-axis, and if this coordinate was the position on a unit circle, the x, y coordinate, x and y coordinate, is the same as our adjacent side length and our opposite side length. So we've got the y and the x coordinate. If I needed to find the y coordinate divided by the x coordinate to represent our tangent function, that's simply the sine value divided by the cosine value. So sine squared divided by cosine squared is indeed going to be tangent of theta squared. Cosine squared divided by itself is going to be the number 1. And 1 divided by cosine, well, that's just the reciprocal of cosine. And we learned that the reciprocal of cosine is known as secant. So the reciprocal of cosine squared is known as secant squared. And here, too, is another Pythagorean identity. Now, for one final example, if I had taken sine squared plus cosine squared equals 1 and divided by sine squared instead of cosine squared, we'll see our third set of Pythagorean identities. So in this case, sine divided by sine is 1. Cosine divided by sine is cotangent. And 1 divided by sine, or the reciprocal of sine, is cosecant. And here, too, is another extension of the Pythagorean identities. There are many, many trigonometric identities that have been computed and determined over the years. We will try to memorize a handful of them, but also it's worth noting that it's a good idea to reference others. And several textbooks will actually publish different trigonometric identities that are useful and used in reference in different sections of their class. And I anticipate doing the same for upcoming tests, especially during Unit 4 and 5. But within this group, these are all called the fundamental identities. This particular row is also known as the quotient identities, and that's what describes the equivalence of tangent to a quotient of two other trig functions. This group in the second row are often called the reciprocal identities. And then in the third row, well, we've seen these already. These are our Pythagorean identities. And how those might be helpful is in questions like this down below. With practice, you could answer some of these problems without the use of a calculator. For example, tangent of 30 degrees is a result that you should be able to do without a calculator. Tangent of 45 can be done without a calculator because these are angle measures that show up nicely inside of our unit circle. Now, 20 degrees does not fall nicely in our unit circle, so we're going to have to use trig identities in order to rewrite this expression to hopefully solve it or simplify. So let's see what we can do using our identities. Well, I'm going to ignore this tangent 20 for just a second. And what I'm going to focus on is this block here. I see that sine of 20 degrees minus cosine of 20 degrees is provided. Now, 20 degrees is the same angle measure for both the numerator and the denominator. So I'm going to mark that as theta for just a second. And I'm going to look for sine theta divided by cosine theta in our trig identity list above, or from memory at this point. And we're going to see if we can find something that would be helpful for us to replace with. And I don't have to look very far. Here's an example of sine theta over cosine theta. Notice the theta values are used, which implies the two angle measures are the same, and that's precisely what we have here. So what this trig identity here is telling us is that sine of theta divided by cosine of theta can be replaced with tangent of that theta. So that's what I'm going to do. I'm going to take, well, I'm going to leave this tangent angle measure alone. But this block here is now going to be turned into tangent of 20 degrees. And lo and behold, this is pretty easy to solve now. Tangent of 20, whatever it is, minus another tangent of 20, well, that's an object, or that's an item subtracting itself. That's going to end up equaling 0. So while it may not have looked like it at the beginning, and we may not have understood it at the beginning, we see that tangent of 20 degrees minus sine of 20 degrees divided by cosine of 20 degrees certainly should be equal to 0. And we were told to complete this without the use of a calculator, which we've done, but certainly we can check our results with the use of a calculator, and so that's what I'm going to do now. So I've set up that expression in the calculator, and before I press enter, I'm double checking my calculator is set to degrees. So the angle measures inside each of these arguments are 20 degrees and not 20 radians. When I tap enter here, I do get the result of 0. So we were able to do that without a calculator, and now we've confirmed it with the calculator. I think that's a good result. In part B, I don't think we'll be quite so lucky. I don't see anything in this expression that matches precisely what our identities indicate. However, there is a phrase here, 1 divided by secant squared of pi over 12. And you should recognize by now that 1 divided by anything implies that we're talking about a reciprocal here. That's one way to flip a fraction. So this is a reciprocal, or an instruction to reciprocate the secant function. And so I'm going to look at the reciprocal group, and I'm going to decide, well, what is the reciprocal of secant, or secant squared? And here it is right here. Secant and cosine go with one another, so the reciprocal of secant squared is indeed cosine squared. So another way to rewrite this expression is sine squared of pi over 12. We can use grouping symbol here. I tend to show the grouping symbol. Plus cosine squared of pi over 12, because again, this expression is the same as cosine squared. And to take this just a bit further, we recognize that the angle measure pi over 12, call that theta, and this angle measure pi over 12, call that theta as well, are the same. So we recognize this as a Pythagorean identity. And we know that sine squared of some angle measure plus cosine squared of the same angle measure must be equivalent to the number 1. So that tells me that sine squared of pi over 12 plus cosine squared of pi over 12 is equal to precisely 1. So we got our solution without a calculator, but I again will check my answer using the calculator. So let's bring that up. And I should point out here that this calculator does not work well with the syntax written on paper. On paper, it's common for us to write phrases like this, sine squared theta or sine cubed theta. That's perfectly standard. However, this calculator and many computers for that matter don't understand that syntax. So if you're going to have a sine computation that's going to be raised to the second power, it is best to group the sine function or trig function and then put the power or the exponent on the outside. So we're going to type sine of pi over 12 quantity squared, so that's our sine squared of theta, plus a large fraction here, control divide, and we've got 1 over top of another fraction, because I'm going back to the original example here. Sorry, there was no fraction in the denominator, it was just secant squared. So I need a trig function to be squared, so I'll put that grouping symbol and square it right away. And on the interior of that grouping symbol, I'll type secant. So we'll use secant. And inside here, we need a fraction, and it's got to be pi divided by 12. So it looks like I picked up an extra, no I didn't, I thought I picked up an extra parentheses here, but that's complete. This one's complete. I'm ready to execute. However, before I do, I want to make note that pi over 12 is an angle measure, but it's an angle measure represented in radians, not degrees. So I better switch my calculator to radians just to be safe. Remember, on these TIs, they're very easy to do. All you have to do is move your mouse to the top right-hand corner and click that button, click that phrase, and it'll switch between degrees and radians. Now, when I press enter here, you can see that the sum of these two expressions does equal 1, exactly like we had predicted using no calculator whatsoever and only trig identities to simplify. So in the interest of time, I think I'll start wrapping up the video now, and what I'll do is I'll switch over to my answer key, my completed set of notes for these remaining problems. I would recommend that you try them on your own. Use identities in number 39 and 40 to simplify the expression. And then for the problems number 26 and 27 at the bottom, these are examples just like the problem that we had right here at the beginning of the notes today. The only difference this time is that only one trigonometric ratio is provided. So you'll have, in this case, the opposite side length of your right triangle and the hypotenuse. But fortunately for us, if we have two side lengths of a right triangle, we can use the Pythagorean equation to find the third. Once you have the third, you can then report your trigonometric ratios just like we did before. So again, pause the video now, find some time to work on these practice problems, and then come back to this portion of the video to check your work. Thanks for watching.